deflection of the beams. You just go through the problem. A concrete beam having rectangular section 100 mm wide and 300 mm deep. Just write the diagram, cross-sectional dimension you write. Solution. Cross-sectional dimensions are 100 mm wide and 300 mm deep. (300 mm deep) is pre-stressed by a parabolic cable carrying an initial force of 240 kilonewton. Pre-stressing force. Initial pre-stressing force is given as 240 kilonewton. Okay. The cable has an eccentricity of 50 mm at the center of the span and is concentric at the support. Okay, write the diagram. Write the central axis. Okay. What he says is the cable has an eccentricity of 50 mm at the center of the span and is concentric at the support. Concentric at the support is there, which means that there is no eccentricity at the support. Okay. Concentric at the support means there is no eccentricity at the support, and he says that 50 mm at the center of the span. And the profile of the cable is parabolic. So I'll write the parabolic cable with 50 mm eccentricity at the center of the span. Like this. Okay. At the center of the span, say eccentricity is 50 mm. 50 mm. Okay. And it is carrying a pre-stressing force of 240 kilonewton. Pre-stressing force P is given. P is equal to how much? 240 kilonewton. If the span of the beam is 10 meter, span of the beam is given as 10 meter. 10 meter is the span of the beam. Then and a live load of 2 kilonewton per meter is acting on the beam. Live load on the beam is given. Live load on the beam is 2 kilonewton per meter. This is WQ, live load on the beam. Estimate short-term deflection of the beam at the center of the span. Okay, this is the first question. Second question is to find long-term deflection. For that, necessary data is given. Assuming E is equal to 38 kilonewton per mm square and creep coefficient is equal to 2.0, loss of pre-stress is equal to 20% of the initial stress after 6 months, estimate the long-term deflection. This is the second question. Okay. First, initially we'll solve the first question. That is, we'll solve for short-term deflection. Okay. So first one you write short-term deflection. Short-term deflection. So this short-term deflection is the combination of deflection due to dead load, deflection due to live load, and deflection due to pre-stress. Now, initially we will find deflection due to dead load. Deflection due to dead load. Deflection due to dead load we will find now. Okay. Intensity of the dead load we have to find first, correct? Wg is equal to R self-weight of beam Wg is equal to cross-sectional area multiplied by density of the concrete. Density of the concrete. So cross-sectional area is It is given as 100 mm by 300 mm. In terms of meter, it is 0.1 into 0.3 into 24 kilonewton per meter cube is the density of the concrete. If you do that, the intensity of the dead load is 0.72 kilonewton per meter. Okay, which is equal to 0.72 Newton per millimeter. Okay, by this we got the dead load. Now you can easily find deflection due to dead load. Okay, the dead load intensity is how much? 0.72 Newton per millimeter, which is acting over a length of how much? 10 meter means 10,000 millimeter. In terms of millimeter, we need the data because finally we have to get the deflection in terms of mm. 10,000 millimeter. Okay, and it is simply supported. Okay, therefore we have the formula deflection due to dead load. Okay, for a beam simply supported carrying UDL, the formula is pi by 384 into WG, in this case L raised to 4 by EC into IX. EC into IX. And EC is given. How much it is given? 38 kilonewton per mm square. EC is equal to 38 kilonewton per mm square. In terms of Newton per mm square, it is 38 into 10 power 3 Newton per mm square. Okay, and length is 10 meter, nothing but 10,000 millimeter. And moment of inertia Ix is equal to BdQ by 12. So B is 100, D is 300. So 100 into 300 Q by 12. For rectangle, moment of inertia is BdQ by 12. So answer is 225 into 10 power 6 mm to the power of 4. Okay, substituting everything, you will get the deflection due to dead load. Therefore, delta DL is equal to 5 by 384 into WG is how much? 0.72 Newton per mm, 0.72 into 10,000 to the power of 4 divided by EC, 38 into 10 power 3 into IX, 225 into 10 power 6. Therefore, deflection due to dead load is equal to, it is 10.96 millimeter. 10.96 millimeter. Plus sign indicates that deflection is in downward direction. Now we got deflection due to dead load. Now we'll calculate deflection due to live load. Second one, B, calculation of deflection due to live load. Deflection due to live load. Okay, the live load intensity is given. How much it is given? 2 kilonewton per meter. WQ is given as 2 kilonewton per meter. In terms of Newton millimeter, it is 2 Newton per millimeter. So it is same beam carrying the UDL, the live load of 2 Newton per millimeter. 10,000 millimeter is the span of the beam. Therefore, deflection due to live load. Same formula will be there because loading condition and the support condition are both are same. 5 by 384 WQ L raised to 4 divided by EC into IX. Therefore, 5 by 384 into WQ is 2 into 10,000 to the power of 4 divided by EC. 38 into 10 power 3. 38 into 10 power 3 into IX. 225 into 10 power 6 into 10 power 6. So by this we'll get deflection due to live load. Please calculate the answer. Deflection due to live load. And check your answer. It is 30.45 millimeter. 30.45 millimeter. Again, we got positive sign which represents the deflection is in downward direction. Okay. Now deflection due to dead load is calculated. Deflection due to live load is calculated. The last one, deflection due to deflection due to pre-stress. Deflection due to pre-stress or pre-stressing force. Just see the nature of the cable profile. It is parabolic in nature. Okay, I'll go to the theory part. So if it is a parabolic cable with zero eccentricity at the support and some eccentricity at the midspan, this is what the nature of bending moment diagram. Correct? This one. Okay, zero bending moment at the support and PE is the bending moment at the midspan. I'll write the same diagram now here. Okay. So here the intensity of the bending moment is P into E. Pre-stressing force P is how much? It is given. Pre-stressing force is 240 kilonewton. 240 kilonewton means in terms of Newton, it is 240 into 10 power 3 Newton into eccentricity at the midspan is 50 mm into 50. So if you calculate this, you will get the answer as 12 into 10 power 6. Okay. And divide the BMD into equal parts, 2 equal parts. And consider the half of the BMD. Half of the BMD. For further calculation. Okay. Now let G be the centroid of the figure parabola. So what is the formula here? So here the total length of the beam is given as 10,000 mm. Correct? 10,000 mm. So half of the length will be 5,000 mm. 5,000 mm. So base width of the parabola is 5,000 and height is 12 into 10 power 6. So here the distance of the centroid. Okay, distance of the centroid here. This distance will be from the extreme edge. What is the formula? What is the formula here? It is 5 by 8 of L. 5 by 8 of L. 5 by 8 of L means 5,000. 5 by 8 of 5,000. Okay. Now we will take that generalized formula, that is deflection due to pre-stress is equal to area into x bar divided by EC into Ix. Okay, now you calculate the area of the parabola. Area is equal to, formula is 2/3 of base into height. 2/3 of base is 5,000 into height is 12 into 10 power 6. 12 into 10 power 6. By this you will get the area. Okay, let me calculate it. So it is 2/3 of 5,000 into 10. 2 into 5,000 into 12 into 10 power 6. Okay, divided by 3. Divided by 3. So 4 into 10 power 10. Answer is 4 into 10 power 10 mm square. Okay, the x bar is 5 by 8 of B. I will change the notation here. B. 5 by 8 of B. So 5 by 8 of B is 5,000. 5,000. 5 by 8 of 5,000 means how much? So 5 into 5,000 divided by 8. 3125. 3125. 3125 mm. Okay. So delta PS is equal to, substitute now, 4 into 10 power 10 area into x bar, 3125 divided by EC into IX. EC is how much it is? 38 into 10 power 3 into 225 into 10 power 6. 225 into 10 power 6. So if you calculate the answer, it will be, and one more important thing here, negative sign for the area. Negative sign for the BMD. Okay, because the full cable is below the neutral axis, it will cause fogging bending moment. Therefore, the sign is negative here. Negative. Okay. Negative sign I have taken. So for area, you take negative sign. So minus here. The final answer is minus 14.61 mm. Minus 14.61 mm. Okay, or else you can directly use this formula. Minus 5 PE, 5 by 48 PE L square by EC into, if you are able to remember this formula. Okay, otherwise you follow this method, area into x bar by EI, which is very simpler and easy to calculate. Okay. Now we have calculated deflection due to dead load, live load, and the pre-stress. Therefore, the net deflection is equal to, therefore, the net deflection is equal to, deflection due to dead load is 10.96, 30.45, minus 14.61, which gives how much? 26.8 millimeter plus 26.8 millimeter, which represents deflection is in downward direction. This is the net deflection. This is short-term deflection. Okay, to this we have calculated the short-term deflection. Next, what we have to calculate? There is one more question in this problem to calculate the long-term deflection. The necessary data for calculating the long-term deflection is given in the problem. Okay, second one, long-term deflection. Second one, long-term deflection. We have the formula delta is equal to delta IL plus delta IP into loss ratio into 1 plus pi. 1 plus pi. So delta IL is nothing but deflection due to only loads, live load and the dead load. Deflection due to dead load is 10.96, deflection due to live load is 30.45. So 10.96 plus 30.45, which gives how much? 41.41 mm. Then delta IP is nothing but deflection due to pre-stressing force, that is 14.61 minus 14.61 millimeter. Then what else we need? We need the loss ratio, correct? Loss ratio means here what is given? Loss of pre-stress is given. Loss of pre-stress is how much it is given? 20%. 20% is the loss of pre-stress. Therefore, the loss ratio will be the loss of pre-stress is given as 20%. Means in 100% pre-stress, 20% is the loss. The remaining pre-stress will be equal to, therefore, the final pre-stress or the remaining pre-stress will be equal to, or the final pre-stress you calculate. Final pre-stress will be equal to 100 minus 20% means 80%. 80% is the final pre-stress. Are understanding? Initial pre-stress, if you assume it as 100%, in that 20% loss has happened. 20% loss has happened means the final pre-stress will be 80%. Final pre-stress will be 80%. Correct. Therefore, the loss ratio which is equal to PF by PI. Final pre-stress is 80. Initial pre-stress if you assume 100, so it is 0.8. It is 0.8. Or else you can calculate this 80% to digit. If you convert 80 by 100, it will be 0.8. Like that also you can calculate the loss ratio. Okay. And pi, creep coefficient. It is also given in the problem. How much it is given? Creep coefficient 2.0. Creep coefficient is equal to 2.0. Therefore, delta is equal to long-term deflection is equal to delta IL 41.41 plus delta IP minus 14.61 into loss ratio 0.8 into 1 plus pi, 1 plus 2. By this we get the long-term deflection. If we calculate, it is 89.166 millimeter. Okay, plus sign represents the deflection is in downward direction. Okay, so this completes the solution of this particular problem. So if you have got any doubts at any point of calculation, you can ask students. Any doubts here in the calculation? Okay, thank you.